Hi, so today we're going to be talking about corrosion. So what is corrosion? Well, corrosion undergoes the same electrochemical process that happens in a galvanic cell, like the one on the right here. So electrons, they leave the anode and they move in the direction towards the cathode in a closed circuit, which is the same process that happens in corrosion. A main difference between corrosion and this galvanic cell is that corrosion is generally a bad thing, while galvanic cells are a good thing and are used to generate electricity. So when we look at the corrosion of iron, we have two half reactions to consider. First, iron 2 plus 2 electrons yields iron solid, and that has a reduction potential of negative 0.440 volts. The other half equation to look at is O2 plus 2H2O plus 4 electrons yields 4 hydroxides, and that has a reduction potential of 0.401 volts. So now to get the full reaction, the whole equation, we want to balance the electrons so we could cancel them out. So to do that, we times the iron half reaction by -2, giving us 2 iron yields 2 iron 2 plus 4 electrons. And from that, we could get the full reaction, 2 iron plus O2 plus 2H2O yields iron 2 hydroxide, which quickly converts to iron 3 hydroxide, which is generally associated with rust. Iron 3 hydroxide then eventually will dehydrate and turn into iron 3 oxide hydrate. And so it's these three compounds that are all associated with rust. So here's just a diagram that I made to help illustrate how rust is formed on iron. So this gray area is the iron, and this blue is a water droplet sitting on top. And so what happens in the middle is that the iron acts as an anode, spontaneously oxidizing into iron 2 plus. That is from this half reaction, it's a bit cut off, this half reaction right here happens right here. And so the electrons then travel over here, right where oxygen is able to come in contact with the surface of iron and with water. And so over here, the second half reaction takes place. And this area acts as a cathode. So then the iron 2 plus and the hydroxide are able to interact together, and they form iron 2 hydroxide and iron 3 hydroxide, and ultimately they form the layer of rust that sits on top of iron. So let's look at the two half reactions again for the corrosion of iron. To calculate the cell potential energy, we need to subtract the anode's reduction potential from the cathode's reduction potential, and that gives us a cell potential energy of 0.841 volts. And if we try to calculate the RT-ZF at standard conditions, we get 0.063 volts, which is much, much smaller than 0.841 volts. So this basically shows us that it doesn't really matter what the temperature and pressure is, this reaction is always going to be spontaneous. So what affects the speed of corrosion? Well, acidic environments actually speed up corrosion. So if we look at the corrosion of iron again, we have the same first half reaction with iron, but we have a different half reaction with water. So now because it's in an acidic environment, the half reaction is O2 plus 4 protons plus 4 electrons yields 2 H2O. And so this has a reduction potential of 1.229 volts. So in an acidic environment, the overall cell potential energy is actually 1.669 volts, which is almost double the cell potential energy in the normal state. So this will mean that this reaction happens faster. So another thing that speeds up corrosion is the presence of electrolytes. Electrolytes are minerals dissolved in a liquid that can carry an electric charge. For example, salt water is an electrolyte. The presence of electrolytes allows metals to more easily give up their electrons and oxidize, which results in speeding up the process of corrosion. So I have a picture on the right of a ship here, probably in salt water, and it is very corroded, and I would imagine that the salt from the water is speeding up this process. Lastly, higher temperatures and pressures generally speed up electrochemical reactions, and therefore they could speed up corrosion. So what are some ways that people prevent corrosion? Well, one way is using a physical barrier, such as a coating of paint, oil, or copper that works by shielding the metal from the water and oxygen, and therefore stops the electrochemical reactions from taking place. Cars usually use a physical barrier, such as oil and paint, to protect the outside from corrosion. Cars also use a technique called passivation, which is when the steel on the car is meant to form a patina, which is when the surface corrodes in a way that protects the steel underneath from further corrosion. So this is what is meant by stainless steel. For example, stainless steel utensils, they have undergone a controlled passivation, which is they've corroded on the surface, but in a way that protects the rest of it from corroding further. Rusting on cars is particularly significant at the bottom and around the wheels. And there's two reasons for this. One is that this area is chipped away at with rocks and debris, exposing the steel to air and water. Another reason is because the salt from the road mixes with the water and forms electrolytes. And the electrolytes were able to speed up the process of corrosion in this area, making it corrode faster. Another way to protect against corrosion is galvanizing. And this works by coating the metal with a substance with a lower standard reduction potential, such as zinc. So here we have iron and zinc has the lower reduction potential. So with a zinc coating, zinc acts as the anode, and iron acts as the cathode. This means that even when the iron is exposed to the air, the zinc will corrode first. So in this case, zinc is called the sacrificial anode. Galvanizing is commonly used in construction projects for various purposes such as steel beams, piping, and building frames. Another form of cathodic protection is you can connect the sacrificial anode to the metal through a wire. This works because of the same reason that the sacrificial anode has a lower standard reduction potential and therefore will undergo oxidation. Commonly, magnesium is used in this form of cathodic protection, and electrons leave from magnesium from it oxidizing and go towards the protected substance. One more way of doing this is by adding a battery to the circuit. This allows you to use any piece of scrap metal as the sacrificial anode. So the battery will send charged electrons from the scrap metal. It'll take electrons from the scrap metal and it will send it to the protected structure. Cathodic protectors are used in pipelines, steel storage tanks, boats, and various other metal objects. So one interesting example of corrosion is the Statue of Liberty, which is made out of copper and was originally brown. Corrosion is what turned the Statue of Liberty to its green, familiar color through a series of redox reactions. First copper reacted with O2 from the air and formed copper oxide. Then, due to the burning of coal, CO2 and SO3 were present in the atmosphere in high enough amounts to lead to the following reactions. With copper reacting with CO2 and water and SO3, it created these following compounds. And it's these compounds that had the color green, blue, and green, leading to this bluish-green color of the Statue of Liberty. Luckily, copper creates a protective layer when it corrodes, which stops the Statue of Liberty from further corroding. So hopefully you now have a better understanding of how corrosion works. In this video, you have seen how corrosion works using the corrosion of iron as an example. We have looked at what factors affect the speed of corrosion, such as acidic environments and electrolytes. We have also looked at ways to prevent corrosion, such as physical barriers, galvanizing, and cathodic protection. And lastly, we have looked at the Statue of Liberty being a famous example of corrosion.